At the end of the last video, we left off at a point where we were contemplating whether or not the value of 0, x equals 0, that critical number was going to produce a local max or local min for the graph of the original function, that is the quartic function. If we look back at what we had done, we once again found the critical values. We had done this already, but we determined that 0 and 6. We dealt with 6, and then we ended up performing what we call a first derivative test to the value or critical value of 0. Please take note that you've already done first derivative tests when you were searching for maxes and mins in the last lesson. So for instance, let's just do a quick sketch here. That is a sidebar sketch. Just going to come off over here in the corner for now. And let's say, for instance, that we had a function that had a shape that is somewhat like this. Okay, and at a particular value of x, call it here, let's say at that point the value of c is a critical value for us. Okay, so what you can see is that on either side, very poorly drawn, but the slopes of the tangents there are both negative, which means that that function is decreasing. Okay, so it's decreasing on that interval. And let's just say arbitrarily, it's an interval AB. Okay, so a variety of different situations exist, right? These are both negative. We could come up with several others, but the point that is really important is the fact that if you look at the slopes of the tangents both being negative, okay, that relates back to this graph of this cubic function. Okay, this is f prime at x. Because we ended up with negative values on either side of the critical number, when f prime at x is negative, right? Remember that when f prime at x is less than 0, the function is decreasing. Okay, thus, more importantly here, in order to have a local min or max, the derivative, first derivative, just put first, must change sign. Okay. In this case, when we tested around the critical value, we ended up getting values of minus 20 on either side. So that corresponds or correlates to this particular situation here. So what we can then say is that since the first derivative f prime at x does not change sign at a critical value c of 0, then c equals 0, or for that matter x equals 0, does not produce, okay, does not produce an extreme value, a local max or min. So that simply validates what we had already figured out in a previous example. At 0, we had an inflection point. Okay. Doing a first derivative test, searching for maxes and mins, we've simply been able to simply been able to, looking for the word here, will more or less prove that it is not an extreme value. Okay? So to wrap this up, what we'll do is, using all of the information we've gathered so far, we're going to sketch a graph of the function. Okay? So let's first think about things that we already understand about quartic functions. If we look at the lead coefficient, okay, here we have a 1, so a is greater than 0. What that implies is that the quadrant flow is from quadrants 2 to 1. Okay, so recall that quadrant 2 is here, quadrant 1 over here. So we know that the function will end in this direction as well as over there. If we think about zeros, okay, that is places where it crosses the x-axis, we had determined already that we had an inflection point at 0, which just so happens to be an x-intercept as well as a the y-intercept. Other zeros, though, okay, because a quartic function can have at most 3 zeros, that is at most 4 zeros, and at most 3 turning points. If we take the function f at x and we were to factor out an x cubed, what we would see is that this equation here, that 0 equals that for all x belonging to the set of 0 and 8. So 8 is also a 0. Let's just place that over there. Now, let's consider some of the other information we have available to us. We had shown that at a value of 6, x equals 6, that there was a local minimum. Okay, so that local minimum, let's go back and see what its y value was. And we had shown minus 432. So let's say we'll break the axis here somewhere, and we'll put 432 down here, say. So 430 roughly. So 6 minus 432. Okay, so with that being a local, and in this case, not only local, but absolute maximum, because all of their minimum, because all of their y values are greater than that. So we understand that part of the graph will go through there. We also had determined there was an inflection point at x equals 4. Okay, now whether or not we had derived its y value is yet to be seen. So for that, let's figure that out. Okay, so for the inflection point there, so f of 4 would be 4 to the 4th minus 8 times 4 cubed. So let's see, 4 to the 4 minus 8 times 4 cubed. Okay, with that announcement out of the way, let's evaluate here. So 4 to the 4 should, oops, that's squared, but to the 4th is 256. And let's take off 8 multiplied by 4 cubed. And we end up with minus 256. So at 4 and minus 256, let's just ballpark that and say it's here. So that was an inflection point. So the function is going to change from concave down to concave up. That is reading the graph from left to right. So from concave down to concave up. And then we saw that at 0, it too was an inflection point. So from there, we're going to transfer from concave down back to concave up. Now, to be a little more specific, we could try to figure out a particular coordinate over here to allow us to be more specific in our sketch. So there you have it, both second derivative tests, first derivative tests, trying to figure out inflection points as well as where local maxes and mins occur. So all of these put together, okay, with a few more tools we'll develop over the next couple of days will help us to more accurately sketch a variety of different functions.